This is backprop part 2. Um, I'm looking at my iPad. I have a bad feeling. I didn't save. I didn't save the drawing from last video, so it's just gone. Um, so let's do a new board. Um, Off the top of my head, where'd we leave off? Logistic regression, partial derivatives. We spoke to VaultChat. VaultChat gave us the context such that we could try to do it for um, VaultChat gave us the context such that we could do it for a neural network. We're supposed to do a neural network today, and then ideally, if we're able to do it in only 2 parts, then we actually get it to the LLM propagation today, which would be really, really fantastic. So, I'm going to immediately swap to the iPad and see if I can um, the logistic regression in formulaic notation, and then do its partial derivatives with respect to W and B, and then I'm going to draw a neural network in that same formulation, do the same derivation, but it's just be a simple extension for from logistic regression. Um, the mistake I'd made for logistic regression is like what I was thinking about for logistic regression is like multi-headed logistic regression, I guess. Um, but that's fine. Um, is multi-headed logistic regression, and then I want to do neural network, and then we can ask questions about. Then I can attempt to do the same formulaic representation of of a large language model, and then like tweak at it and see what happens when I try to do things like attention and get completely lost, and then we can cue David back in. So let's see what that looks like. Full screen, exit full. Ooh, that's a far better transition. Um, I might keep that in mind for future videos. Is I can go full screen with like the iPad thing, and you guys never have to see my awesome actual um, home screen. Okay, so let's start with black. Black is fine. Um, what are we going to draw? We have so our goals are district regression and classical. It's like let's take our time. Let's not be discouraged by using time. Um, we have a sigmoidal function, which is 1 over 1 plus e to the minus x. Haha, I remembered. Oops. Um, and it looks like this. No, it doesn't. It looks a lot closer to that. Where this is at 0.5, this is 1, and this is 0. If you can imagine, this is x, this is sigmoid of x. I should probably use a smaller font, or yeah. Um, and x gets really big, then we're going to approach 1. If you can imagine, e to the power of negative infinity collapses to 0, limits towards 0, so you get 1 over 1. And then if x is really small, then e to the x is really big, and then 1 over infinity once again is 0. So that's fine. And then once again, yeah, if x is 0, then we'll get 0.5 because 1 over 1 plus 1 is 1 over 2. Fantastic. So you have sigmoid, and then let me just rewrite it again. It is sigmoid of x equals 1 over 1 plus e to the minus x. And then sigmoid prime of x. Very curious is like, I don't know. I'm not really doing this with anyone else. Is like, I don't know, the notation differences. I wonder how other people write this kind of stuff. Sigmoid of x times 1 minus sigmoid of x. Very convenient. Once again, you cannot see anything I'm writing. There we go. I forgot a parentheses. Okay, that's sigmoid. That's fine. So then, how are we going to represent a logistic regression for a single, let's say, spam, the classic? Okay, let's say we have x. X is a feature vector of characteristics of an email of, let's just do binary, is like gold, SSN, and um, 1. You know what I mean? And these are all binary of whether or not the email included these keywords. So an email that said gold, asked for your social security number, and say you won the lottery or you won anything, a cruise, a vacation, that would be this. And then like there's, I don't know, 2 to the 3, there's 8 possible um, X's. That's completely irrelevant. Um, so we do that. That's our context for X. And we want to predict 3 things. And then this is just like a quick interview question, is importantly, this is, we're doing sigmoid 3 times. We're not doing softmax. So it's not as if you have to choose between one of these things. We're just using the same feature and the same matrix to answer the same question. And even further, I believe um, that the matrix form for doing logistic regression that I'm going to write out is equivalent to just doing multiple isolated logistic regressions. So let's keep going. Is we're going to do y, why does that look dotted? Yeah. We're going to say y equals wx plus b, and actually sigmoid of wx plus b. And if w, depending on how many things we want to um, write, oh my goodness, you still can't see it. Um, depending on if we're doing logistic regression for a single thing or multiple things, w could be 1 by 3, because x is 3, and then b would also have to be a 3 by 1. What? 1 by 3 times 3 by 1 is a 1 by 1. Oh, so b would actually be a scalar. That makes sense. Oh, wait. I don't know how I represent that. B would be a scalar. What's it called? And the w would effectively be a vector, and we will call it a 1 by 3 matrix. And that's going to give us sigmoid for a single single data point. Yeah, sigmoid for the single data point to answer the question why. And the question why is the email spam? I don't know. Was the email sent from this well-known particular scammer group, or was the email sent from this well-known particular scammer group? And once again, importantly, we're not going to do softmax. So for example, they could both say 1. Practically, designing your logistic regression or your model, you wouldn't do that. You would use softmax to force the model to choose between the two, and if it's 50-50, then it's 50-50, but you wouldn't design it like that to have sigmoid that's just less interpretable, you know? But yeah, so like you could have y1, y2, y3 of very similar designs, and then all you would end up changing is w from 3. And technically, just because the way linear algebra works is if you have, again, I don't know who I'm teaching this to, A, B, C, D, E, F, G, H, I. When you multiply this w by x, so let's do 1, 2, 3, is like, it's this row in this column, you know? Which is, and then, and that gives you this, and then you're going to multiply, you're going to add, this is a 3 by 1, yeah, you're going to add it by, x, y, z. you're going to add them by these values, but it's just going to be literally equal to 3 linear equations. We haven't done anything fancy because the way that we're going to apply sigmoid is element wise. So there's no fancy across vector or anything going on. So it's like exactly equivalent. There's no point. It's the same thing. I actually realized that. How about it? Me saying this out loud is my first time realizing that, but it doesn't make it not true. I'm pretty sure it's true. Um, so moving forward, let's see if we can take the derivative. So now we have, this is supposed to be sigmoid of x, and we'll move this because this is our story. Say we're continuing to do the lottery example. I apologize if I'm not noticing. If there's other instances where I'm just covering and talking about something, but like you can't see it, that's my bad. So let's see. I guess I should bias towards putting things at the bottom. I don't like that though. And for whatever the reason, this keeps spawning back. Okay. So we have sigmoid of x equals. Now, classical logistic regression. We have y, vector or scalar, I think this is irrelevant, equals wx plus b. Another question I sort of had, I promise this is worth it. This y, if we were to write it as a function, traditionally, or the way I sort of learn in class is like you would write f of x, and then you'd use this semicolon to denote that w and b are like the parameters that describe the function f. But like x is like the input. But when we're going to do like the calculus, is like you could do y with respect to x, but you can also do y with respect to w and b because they're all variables that we can change that are like interacting. In fact, you know what I mean? So you could write it like this, or you could write it as x with no thingy, xwb. You know what I mean? And like for me, at least the way that like we write calculus and that kind of stuff, that's what this is it's a function of x, w, and b, and then we're taking the derivatives, the gradient, whatever, with respect to w and b, and just not x because we're doing partials, gradient, like completely fine, no one cares. But interesting is this is I don't know, it's like I literally split these. It's like these are parameters and these are inputs, and the idea of a gradient with respect to a parameter, like again, that's what we're doing, like that's fine. I don't know. I just don't have that relationship. So it's a notation question, and I don't have the answer for it because I haven't looked it up yet, and I probably might not. I might at some point. Um. So let's keep going, and we want the partial derivative of y with respect to w. Oh, I forgot sigmoid. Perfect. Okay. Equals by the chain rule the partial derivative of y with respect to the partial derivative of, let's say, what's the word? I'm just recalling what David had wrote is, I think David had wrote that A equals sigmoid of wx plus b. But that's a little bit weird because obviously that's 1, and like we didn't do anything. It's like x and y are the same thing. Um, so hmm, 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 hmm. Let's skip it. I don't think it goes there. I'll have to send a photo. We'll get this graded eventually. Um, so I wouldn't write that. Is This is already 1. This is already 1. So immediately, oh, even worse. I think it's 1 times, I think it's just X transpose. Dare I say that? Dare I say that? I think that's it. And then the derivative of y with respect to b I'm missing something, man. It's 1. But we're not. Who's he? It's like we're supposed to do. It's almost like it's y times X transpose. You know what I mean? It's like you're supposed to do this. You're supposed to do the outside gradient, but that would actually be. Am I stuck already? So like, there's two things I'm stuck on. Is I want to write something like equals over x times x over partial w. You know what I mean? I want to write this and do the classic like, ooh, whatever. I want to do this and do like the classical like just like split out of like multiplying things for like chain rule. And I think this is appropriate. But so like, what I'm missing is that when you do f of x equals g of h of x, is that you write f prime of x equals g prime of h of x times h prime of x. Sorry, again, complete mess, whatever. And like that, the fact that h of x is being plugged into g prime of x isn't being captured when we write this. You know what I mean? Um, but like this is sort of like the habitual way that you do it. So I'm not really sure. Let's see if I can, if I end up taking a photo to ask the question. I'll make it nice for David, but I won't make it nice for you guys. X prime of x equals g prime. Okay. Yeah, I'm confused on the difference. Like, these are both the chain rule, but they look like different things to me. So, we'll check that out. Maybe really soon. I don't know. But this is that, that's a confusion. I don't think I have the answer. Again, how much of this stuff is notation, you know? Um, and in which case, I think I'm already stuck and I should already be asking a question, which kind of sucks. Okay, let's go for it in the interest of time. I have an extremely early meeting tomorrow. Let's see. So I want to take a photo, right? Do I want to take a photo of everything? Can I fit it? I think I can. Oh, you can't see that part. There we go. So get a copy. We'll exit. I'll hide this from you. And then I'll open Vault Chat. Okay. Oh, and then I can also just like read this. Just go back to it. So yeah, that's A. Oh, 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 oh. Because we didn't do loss. That's what we're missing. So this is the first thing. Okay, but then what's um A? Okay, so let's pause. Let's pause. Is with respect to Z. Why are we doing it with respect to Z? Did we do L? We did L with respect to A first, which makes perfect sense because we're supposed to have done loss. Okay, L with respect to A, but we can almost ignore that because from our perspective is that we're doing A with respect to Z. Is that how it does? Yeah. Wait. That's how they did it. They did it. Yeah. That's part of why. That's part of why I'm confused. So this A is like actually would be like something like really ugly for us because um A equals sigmoid of Z, which is our whole equation, and like if you spelled this out, it would look pretty ugly, you know. But like it's packaged well, so it looks nice. Something I was never stellar at. And then from there, yeah, exactly. Z with respect to B is just one, and then Z with respect to W, and Z is that inside. Yeah, with respect to W is just X transpose. And then chaining it all together, B is, yeah, times Z of, yeah. So wait, I'm a little bit curious. Okay, this is the first notation. Is where would my confusion be? Is because A equals a function with an input, and its um its derivative, I would still have its input but multiply it by the output. But to make things work for this chain rule is a function is going to be turned into a variable, I guess. And this is not the best thing to do. So maybe I'll continue to ask these things. Um, so let's see. So many questions. So function turned. I don't have spell check on. To variable, and it makes me happy because I don't get to tell. I don't get told that I spell wrong. Um, let's see. Function get told turn into a variable for notation question mark. I.e. Ooh, am I dialed? See. Oh, um, how do I say equals A? I'll flex my latex a little bit. Equals A. And you would write speaking out loud in my head is not the same as communicating in a video. Um, but yeah, hope I don't know. Maybe you were reading while I was typing. Is yeah. I think it's a notation thing. Like me typing it is sort of helping me clear it up. I'm also confused about. So there's that notation thing. There was one other thing I had. I don't know. Um, the X transpose and oh yeah, yeah. It's like I don't know. I would sort of like formalize. It's like yeah. I think the notation is one of the main things I'm confused about. Equal to a bunch of, and then I think those are my questions. Um, yeah, and then hopefully we can get to the neural network soon because like we're reviewing yesterday. Hi David. I don't know if you remember where we left off, but I just added 3 questions that I have to the back propagation study guide that I have open right now. Um, do you think you could help clarify the answers to these for me? Um, and like I guess yeah, maybe if you could also write if you could do the example for the neural network once we get there. I think seeing that math will help me out, and then you explaining all these notation things, and like sort of like what's going on in the background and how and why we write it like this. I think that would help me out a lot.
I would love to break these down for you. Let us start with your first question about turning functions into variables for notation. When you write the chain rule in introductory calculus, you often write it as f prime of g of x times g prime of x. This gets incredibly messy in deep learning because we have long chains of nested functions, and keeping track of what is being evaluated, where is a nightmare. By defining intermediate variables like z equals wx plus b and it equals sigmoid of z, we can treat every step as a simple relationship between variables. Instead of writing sigmoid prime of wx plus b times x, we write partial L over partial z times partial z over partial w. This variable level notation lets us compute local derivatives step by step, and we just multiply them together until we reach our target. It is exactly how automatic differentiation is implemented in PyTorch. For your second question about why X transpose appears, let us look at the dimensions. Your weight matrix W is a row vector of size 1 by D, and your
Okay.
input X is a column vector.
No, let's take a moment on the first question. When you say the math out loud, it doesn't, I can't see what you're saying. So it would help me out if you sort of spelled that out under the question inside of the actual file. And is what are you implying that what I described as part of my question correct? Like it's for the local single variable, and then we just keep going until we're happy, and like, we could in theory unnecessarily continue to go, but it would all just be a bunch of ones. So it's equivalent to just going as single variable deep as we like, as long as we continue to produce the intermediate. But if you could show like the sort of contrast, like the before and after, and make that picture for me very clear, I think I would appreciate that a lot. And in particular, part of why I'm pushing towards the X transpose and the neural network representation is we're writing this for single variable, and I think the derivatives in math for this is a bit easier for this sort of basic logistic regression. But as we expand to the neural network, like the true matrix representation, I think the matrix calculus is the next level of notation. But first, let's answer the first question.
Yes, you are exactly right. Your intuition is spot on. You can go as deep as you want, and if you went further, you would just be multiplying by 1. I have updated the study guide file to show you the direct contrast. In standard calculus, you write the chain rule using nested functions like f prime of g of x times g prime of x. In deep learning, we assign a variable to every intermediate step, which lets us write the chain rule purely in terms of local variable relationships like partial L over partial A, times partial A over partial Z, times partial Z over partial W. I also added an explanation of how you can theoretically go as deep as you want, but we stop when we reach the actual parameter we want to update, because the derivative of a parameter with respect to itself is just 1. Take a look at the file to see how that looks in math notation.
Okay, I'd mute myself because early mistake. We're recovered from that. So let's see. Yeah, it is exactly. It's like we learned to write it like this. Oops. Oh, I don't know why it has that. We learned to write it like this. This is very classical. I wish it did this with F. I feel like that contrast would have helped. Where are the ticks coming from? It's kind of weird. In deep learning, we have long chains of operations. If we kept writing, of course, the notation would quickly become unreadable. Um, by assigning a variable for every intermediate step, we can write the chain rule purely in terms of local variable relationships. Yes, you are correct that you can go as deep as you want. I think the going as deep as I want is not really useful because you can only go one step further. So I think it was just that was just glaze. Um, and then that was the whole thing. Yeah, where's the X transpose? You're correct that if you can go as deep as you want, define a trivial variable u equals w, then what? No, see, yeah. Okay, so once again, the chance you didn't it didn't help me out. It just did matrix calculus without, telling me how it really works. Um, let's see. Okay, a few things for your so you can just like edit the answer for this part is if you could actually make the contrast examples like, you write the same thing, you write the same letters but in the expansive and knowing form and then in the better deep learning form and you like show the defined intermediate ones. So you do f of g of h and whatnot so that it becomes clear, then you show the intermediates and you show how like it's equivalent and cleaner. Um and then how do I say? Remove the part where we can go one extra step. I don't think that's really of value. And then once you've done that cleanup, I think I would like for you to explain the matrix calculus notation because, for example, y with respect to w being a vector, you know what I mean? Like that, none of that is connected for me. So if you could sort of, you know what I mean? Like slowly, concretely, um, bring me up to speed on on how that stuff works, I would really appreciate it.
I have updated the first answer in your study guide to show the exact contrast using the same variables, showing how the nested function notation compares directly to the cleaner variable-based chain rule. Now let us tackle the matrix calculus notation and why that transpose appears. To build a solid intuition, we must look at the dimensions of our variables. In our logistic regression setup, the weight matrix W is a row vector of size 1 by D, and the input X is a column vector of size D by 1. When we multiply them, we get a scalar Z. When we take the derivative of a scalar, like the law cell with respect to a vector or matrix like W, we want the gradient to have the exact same shape as the original variable. This is a standard convention in deep learning called the denominator layout. Since W is a row vector of size 1 by D, its gradient, the derivative of L with respect to W, must also be a row vector of size 1 by D. Let us look at the chain rule we wrote. The derivative of L with respect to W is the derivative of L with respect to Z, multiplied by the derivative of Z with respect to W. The first term, the derivative of L with respect
Sorry.
to
Um, yes, I would. Two things. Don't ever say math out loud. Just tell me that you updated it inside of the note, and like pause and make sure you like handle your conversating well, so that you like, I don't know, you say something and then you tell me to look and like be prepared for me to take a moment to actually look at what you're saying. Um, but I think I'm starting to see off of the bat of what you were saying is like, if W is a 1 by D um, matrix per se, then its gradient should also be 1 by D. But because it's linear algebra, it's literally X because that's what you know, what's it called? That's just the basic derivative of a coefficient operation. Is if W is the variable, X is the coefficient, then you get the coefficients, but it's transposed. So like, the transpose is coming from W, and then the X is coming from the fact that it's the coefficient for the operations done to W. And I guess that gives me, just taking it a little bit further is um so what does that look like for matrix to matrix relationships?
I have updated the study guide to explain the transpose of X using the shape matching convention. Take a moment to read through that section in the file, and let me know when you are ready to move on to matrix relationships.
Okay, let's see. Um, so exponentials answer. Let's look at the dimensions. Our forward pass we have is W is a row vector. In deep learning, we use the denominator layout convention, which means the gradient of a scalar with respect to a variable must have the exact shape of that variable. The gradient of a scalar. So z is a scalar with respect to um a variable must have the same shape as that variable. Since W is a row vector. Um, yeah, sure, that's fine. But I would like to see more examples of how the denominator layout holds. If we take the derivative of z with respect to W, using standard calculus rules, x acts as a coefficient. However, x is a column vector of size d by 1. To make the dimensions match our 1 by d target shape, we must transpose x. I don't like that whatsoever. Okay. So, a few things. I don't like your explanation for the fact that, you know, x would be the correct thing, but we must transpose for it to match shape. Like, that seems very hacky. That doesn't seem like what the true, doesn't sound like any like true math operation or anything like that. There's got to be a better explanation. And then for the denominator layout, you've said okay, but that's the rule for a scalar. But like, what does this denominator layout convention actually, what's the complete convention? Like, what are the other potential cases? And how do you represent the gradients and whatnot?
I have updated the study guide to address both of your points. First, I replaced the shape matching explanation with a rigorous element by element derivation. It shows how taking the partial derivative with respect to each individual weight naturally produces a row vector of inputs, which mathematically requires the transpose of our column vector.
Okay, let's inspect. You're completely right to to find shape matching explanation unsatisfactory. Blah, blah, blah. It feels like a hack because it's a shortcut that skips the underlying multivariable calculus. Let us look at what is actually happening under the hood. We write z equals, let us write our scalar multiplication for each element. If w is a row vector and x is a column, then perfect. That's what z looks like. Now let's take the partial derivatives of the scalar z with respect to every single individual weight one by one. Yes, we get all the x's. Perfect. Yes, I agree with that. But then what's the shape? Under the denominator layout convention, it's okay, fine. It's a convention on purpose. Maybe that'll help me accept it. The gradient of a scalar with respect to a vector or matrix must have the exact same shape as that vector or matrix. Ah, okay, but that's once again, that's the gradient of a scalar with respect to a vector or matrix. What's the gradient of a vector with respect to a scalar? And you know what I mean? Like all that kind of stuff. Is that even possible? Gradient of a vector. I don't even know if that's possible. Um, since W is a row vector, its gradient must be a row vector. Sure, by convention, and then because we know its values, that gives us its shape. It's a convention. It's fine. The values don't change. It's a shape convention. It's a shape convention. I'm okay with that. Notice that it's a row vector, but our original x was defined by a column vector. To write the row vector using the defined x, we must write x transpose. The transpose is not a hack to force it to fit. It's the mathematically rigorous way to represent the collection of individual partial derivatives in the correct layout convention. Cool. I like that. Okay, the matrix calculus conventions. To clear the confusion about the denominator layout, here's the complete picture of how we organize derivatives in matrix calculus. There are two competing conventions: denominator layout, commonly used in machine learning and physics because gradients match parameter shapes. Yeah, that's exactly how I would use it. Ooh, so as I would say, because gradients match parameter shapes. That's extremely convenient because the literal machine learning is like, yes, why would, of course, they better. I really want them to. And numerator layout, commonly used in mathematics and statistics. Statistics and machine learning also have quite the amount of overlap. So that is very interesting. Very, very interesting. Um, so let's see. Scalar by vector, vector by scalar, vector by vector. There's got to be more than that. So here, how they represent the three main cases. Scalar y with respect to the vector x. Scalar is a column vector. Each element is a row vector. Okay, it says row vector versus column. How do I say it? Derivative of scalar y with respect to vector x. Yeah. Yeah, and I like denominator layout. Okay, cool. Because that makes a whole lot more sense. Um, derivative of vector with respect to a scalar. That's weird because a scalar has a dimension of 1 by 1. So that doesn't perfectly work out. Vector by vector. M by 1. So it's going to protect, yeah, it forms a Jacobian matrix. Does it really? I need to look into more into Jacobians. The Jacobians are so cool. And then the Jacobian conjecture was like disproven, which is like heartbreaking, bro. Like heartbreaking. Like that sucks. That like you can have like what you would think is a like how do I say an injective like transformation, like an actually one-to-one transformation, and you have it most of the time. So like practically speaking, I guess it's not an issue. But the fact that there's no like mathematical guarantee, I really would have appreciated a mathematical guarantee. The idea that like you have a unique transformation, but it's not unique. Whoa. Again, yeah. No good. No good. Let's see. Vector by vector, derivative of this form is a d by n. Denominator layout. Let's see this. X. Denominator layout. X. Yeah. Okay. Denominator layout. I think that would require me to do like actually some like practice problems in order for me to get. In deep learning, we stick with the denominator layout because it allows us to compute the gradient of our scalar loss with respect to a matrix W. Yeah, yeah, exactly. And this is with the optimizer step. Perfect. Yeah, that makes sense. Um, Having the dimensions, I think, is fantastic. And it is, in fact, a notation thing. Um, yeah, I think that notation would take me doing practice problems. So maybe tomorrow is um, practicing matrix calculus. Mm. That's where it's starting to look for me. Um, what time is it? Yeah, this video might end up being shorter, but I think I'm ready for the low key just like to jump to the answer. Um, so let's see. Let's just use full chat. Okay, finish. Okay, so it's just gonna go all the way through, and then check this out. Oh, this guy's got thought through every feature for Vault Chat. Um, oh, this is by layer. G is just going to be your nonlinear activation function. Is it element wise activation function? Okay, cool. Um, this is the representation is like L of G of W. Yeah, classical. That's exactly what I expect. Autograph graph. That's not enough detail though. Backward pass, still no good for me. Um, Same machinery for an LLM? I don't think so. No, I still don't get it. I still don't get it. And so much so that like through the linear layer, sure, whatever, boring. Softmax, who cares? Boring. None of those things are hard though. Self attention. Yes, that projection, bro. I don't think that leans to a mathematical operation. Okay, I'm gonna ask David just like um quick question. So for LLMs, when we do autograd and the graph and stuff, um, for multi-headed attention and like normal attention, things like the causal mask and um splitting and then um combining or concatenating matrices are not like native calculus operations. So how is it that we're able to do gradient descent when those are part of our function? Doesn't it, you know, turn the transformer into a non-differentiable function? How is this handled?
I have updated the study guide to answer this exact question. I added a section at the very bottom of the file explaining how AutoGrad handles non-calculus operations like masking, splitting, and concatenating. Take a look at the new section in the file and let me know if the way AutoGrad routes those gradients makes sense.
Can you also just say it to me out loud, please?
The short answer is that AutoGrad treats these operations as routing mechanisms rather than mathematical transformations. They do not change the values of the numbers. They just change where those numbers go. For example, when you split a matrix into multiple heads or concatenate them back together, AutoGrad does not need to do any calculus. It just tracks the indices. During the forward pass, it copies the values to new memory locations. During the backward pass, it does the exact inverse. It routes the incoming gradients back to their original
What
positions.
about okay, but what about things like the causal mask, where like we're literally dropping numbers? Is that going to be an inference time thing or something? Or like, we do the gradient across the non-maxed matrix? That doesn't make sense.
The causal mask is actually applied during training, not just at inference. We implement it by adding negative infinity to the mask positions before we run the softmax. When you exponentiate negative infinity in the softmax, those mask positions become exactly zero. Since their forward activation is zero, AutoGrad's derivative for the softmax naturally multiplies the incoming gradient by zero for those positions. So the gradients for the masked out tokens are simply blocked and never flow backward.
Oh wait, sorry, I think I spaced out for a little bit. But you're telling me that when we mask them, we don't mask them as zero, we mask them as infinities so that their gradients are then zero. And because if we multiply the change by zero, that applies the mask in the gradient as well as in the actual computation.
Yes, exactly. We set them to negative infinity right before the softmax. Because the softmax exponentiates its inputs, e to the power of negative infinity becomes exactly zero. Since those mask positions have a forward value of zero, the derivative of the softmax naturally multiplies their gradients by zero. So the mask is perfectly preserved in both the forward and backward passes.
Hmm.
Take a second to let that sink in. It is a really elegant trick because it means we do not have to write any special gradient logic for the mask. The standard calculus of the softmax function handles the masking for us automatically.
But what about the step in which the mask is applied? Like, that's not normal calculus, you know what I mean?
Ah, I see what you mean. You are asking about the actual step where we add negative infinity to the matrix. Mathematically, adding a constant mask matrix is just addition. The derivative of a sum, like a plus b, with respect to a is just 1. So AutoGrad just passes the gradient straight through that step unchanged.
Wait,
The
so
math
they add so the operation is to add a matrix of sort of like a complement to the mask of a bunch of negative infinities that gets added to the mask into the scores matrix, which has no effect on the ones that we care about, but it completely masks out the ones that we do want to be masked out. But the operation is technically the addition of negative infinity, which just again masks everything to negative infinity.
Exactly. You nailed it. The operation is just adding a static matrix of zeros and negative infinities.
Okay, so I think that's technically the main question I had. So that's very interesting. That's a very cool. That is a very crazy trick. Um, so yeah, outside of that, and then concatenating, I guess, doesn't really matter. It's like, yeah, the concatenating is just changing where it is. It's still the same gradient with respect to this thing. You know what I mean? How it's represent how it's represented and ordered as a tensor. I believe that's fairly irrelevant. That's why there's literally a convention of um, numerator versus denominator layout. Because the values are the same, but how are you going to structure it? Um, and then yeah, the denominator makes sense. Okay, perfect. So I think tomorrow we should be trying to do matrix calculus because that notation is like so like practice problems. That's very strange. Um, but soon is like we're so like as the week comes to an end is like well I want to and need to code. Um, when are we're you know when are we closing in on the reproduction of the paper, bro? Because this isn't helping, or it's helping. Like I'm learning, but like you can spend how do I say like when we anchor on like the practical goal and like the deep motivation and whatnot, the motivation isn't to learn a bunch of stuff. I can spend a lot of time learning a bunch of stuff. Um, it's about like learning the right things and like actually like practicing and doing the right things. Um, so I can get excited and have fun. And like this is sort of like a weird new idea in a way. Is like I can get distracted by having too much fun learning new stuff. You know, I feel like you would almost never tell that to a child. Like explore, have fun. Blah, 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 blah. But I should learn the right thing. You know what I mean? Is this is such a rich new space for me that no matter what I do or try to do, I'm going to get excited from learning. So, what am I doing to make sure um, that the thing I'm learning is also points towards the level points towards the execution of something. And in this context, the execution should be of a run of a paper. But hopefully, again, the autograd graph is something that we're going to be passing through our optimizer, and um, I want to be a little bit more in touch with my autograd graph. Like we can't be completely out of the loop of that. So I do think this is important. Like what's it called? Because the matrix operations we're going to do, and then, yeah, well, PyTorch is going to do it all for me. And very interestingly, I wonder, yeah, is like mask. I wonder if PyTorch has a mask operation. You know what I mean? So that it knows to do the addition instead of I actually add in infinities matrix, you know? And I would also really, I think a good exercise, even though this is like a learning tangent for fun, is if I could get the formulaic representation of a single transformer large language model, whew, like I spell that whole thing out, that's something, you know? And if I can write it in like matrix form, I think I think that's the pinnacle of like, oh no, dude, that transformer is in the noggin. So yeah, okay. So I'll see you tomorrow. Hopefully I'm just gonna do keep it simple is matrix calculus practice problems. Keep it short and sweet. I will see you